It is Ryan Seacrest here. There was a recent social media trend which consisted of flying on a plane with no music, no movies, no entertainment. But a better trend would be going to ChumbaCasino.com. It's like having a mini social casino in your pocket. Chumba Casino has over 100 online casino-style games, all absolutely free. It's the most fun you can have online and on a plane. So grab your free welcome bonus now at ChumbaCasino.com. Sponsored by Chumba Casino.
No purchase necessary. VGW Group. Void where prohibited by law. 21 plus. Terms and conditions apply.
This is the Logic of Risk. I'm Pasquale, and I welcome you to this new episode, number 16. Before we begin, a quick notice. Next week, I will be traveling for work matters first, and then for my birthday, so there won't be a new episode. Episode 17 will be released on May 3rd, so you can relax a bit. Or rather, at the end of the episode, I will recommend an interesting reading, so you have some homework. But it's not mandatory. Don't roll your eyes. Now, let's get started. In the last episode, we introduced the CDF of a random variable x, and we said that from it we can obtain plenty of information about x. Let's see. By inverting the cumulative distribution function, and purists will forgive me for the inaccuracies, you obtain the so-called quantile function, usually denoted with an uppercase q or an uppercase f raised to the minus 1. Without getting lost in details, the quantile function answers a question that is the inverse of the one answered by the CDF. The cumulative distribution function f of x tells us the probability of observing a value less than or equal to a given lowercase x. The quantile function does the opposite. It tells us which lowercase x corresponds to a given cumulative probability p. In our investment example from the last episode, I might ask, what is the first value of x that corresponds to a cumulative probability of 60%? And the answer would be 0. In technical terms, we would say that 0 is the 60% quantile or the 60th percentile. But since we are talking about investments, I could also ask what is the threshold value that splits the total probability in two, such that 50% of the outcomes are lower and 50% are higher. For us, it would be minus 1. And that value, which leaves 50% of the probability to the left and the same amount to the right, is called the median. It is indeed one of the most famous quantiles. A quantile, or percentile, as you have understood, is a value of x that corresponds to a given cumulative probability. Another famous quantile is the value at risk, an ugly name given by the quants at JP Morgan to a simple tail quantile. Renaming things is a quirk many have, especially when they have to sell you something. Returning to value at risk, or VAR, given a specific probability value, let's say 95%, the 95% value at risk is nothing more than the value of x such that 95% of the probability lies to its left and 5% to its right. So, if I have a distribution of losses in which losses are non-negative quantities represented by a given cumulative distribution function, the 95% var will simply be the first value of x for which the uppercase f assigns a cumulative probability of 0.95. Now, if the cumulative probability at lowercase x is 95%, what is the probability of observing a value greater than lowercase x? Well, it will be equal to 1 minus the probability of observing something less than or equal to small x. That is 1 minus 0.95. which is 0.05 or 5%. Given the cumulative distribution function F, I can then define a new function, uppercase S, equal to 1 minus uppercase f, which I will call the survival function, and which assigns to each lowercase x the probability of observing a greater value. In our earlier investment example, if I take 0, what is the value of the survival function at 0? It will be 0.4, that is 1 minus 0.6, which we saw was the value of the cumulative distribution function at 0. You see, it doesn't take much to introduce objects such as the CDF, the quantile function, or the survival function. On my website, thelogicofrisk.com, I have prepared a small visual summary for you. There is only one last important function associated with a random variable x. It is a function that, from a mathematical point of view, is obtained as the derivative of the cumulative distribution function uppercase f. Do you remember the exponential random variable? We said that its CDF is 1 minus e to the minus lambda x for non-negative values of x. Here, if we calculate the derivative with respect to x, we obtain lambda e to the power minus lambda x. While we use the uppercase f for the cumulative distribution function, for its derivative we use the lowercase f. The function lowercase f of x is what we call the density function, or PDF, probability density function. To be precise, it is called the density function if the random variable is continuous, and probability mass function if it is discrete. But if you always say density function or PDF, it is fine, it is understood from the context. In this podcast, I'm not interested, at least not for the moment, and especially not if it is not strictly necessary, in boring you with derivatives and integrals. So we won't spend too much time on the density function as the derivative of the cumulative distribution function. What I'm interested in is explaining the meaning of the density function. If the cumulative distribution function gives the cumulative probability, the density function gives that point probability. But here you have to be careful, even if we are a bit rough around the edges as we are. In the case of discrete variables, what has been said is entirely true. The probability mass function in our example tells us that the probability of observing -1 is 50%, of observing 0 is 10%, and for 2 we have 40%. It also tells us that the probability of observing -0.5 or 3 is 0. For a Bernoulli variable, the density function tells us that the probability of observing 1 is a generic probability p, and that of observing 0 is 1 minus p. Meanwhile, the probability of observing 0.5, -4, or 7 is 0. In a discrete variable, each possible outcome has a well-defined probability mass, which is why we speak of a probability mass function. The total probability, which, as we know, must be equal to 1, is divided over a certain finite or countable number of events, and we can see it split into many small columns, much like in a histogram, if you are familiar, and each column is a height that tells us how much probability mass there is at that point. For a continuous variable, the matter is not so simple, because the points, even in a small interval, are infinite. So the total probability equal to 1 must be distributed over an infinite number of values. That's why we say that the mass at a single point for a continuous random variable is 0. However, the density can tell us what the probability is of falling within any small interval around the value of our interest. Simply put, from the density we cannot derive what the probability is of getting exactly 4.62, but, for example, what the probability is of getting a value between 4.61 and 4.63. Of course, the same value could also be obtained via the cumulative distribution function, taking the value calculated at 4.633 and subtracting the one calculated at 4.61. Try it with paper and pen to see why. But let's say that with the density, when well defined, it is often easier to work. For now, we won't add anything more. So, summarizing, we have talked about random variables and some functions relevant to describe their meaning. We mentioned the CDF, the density function, the quantile function, and the survival function. If something is not clear, re-listen to the recent episodes, and if you have any questions, write to me. Regarding random variables, we said in general that they are variables that can take on different values, each with a given probability, corresponding to different random events. These random events are those described by the probability space omega f p. To be more precise, we should say that a random variable x is in fact a function that transforms the original probability space omega f p into a new probability space, usually indicated by the triplet r, b, px, where r represents the real line or a subset thereof, indicating the values that the random variable x can take. B is the so-called Borel sigma algebra, that is the space of events of the random variable x, represented as the set of all open subsets of R, and finally Px represents the probability distribution of x, as described, for example, by its cumulative distribution function. But at the end of the day, it's like saying that the original probability space omega fp is in English, and for me being Italian or for you being German, it is better to work in the language that is more familiar. So we use the random variable x to translate it into another probability space in Italian or German, which will be the space RB px. Without going into further details for the moment, I hope the basic idea is clear. Just know that the new probability space RBPX is the one in which we quantify risk, that is, the damages and their likelihood. This is also why, in risk management, it is sometimes called the loss space, to distinguish it more quickly from the original probability space. We have also talked about the support of x and defined it as the set of values that our random variable can take. This set can be the entire real line, if x can vary continuously from negative infinity to positive infinity, or any subset of that line. Now, connected to the concept of support, there is a fundamental distinction that, alas, even many experts, or so-called experts, ignore, using as synonyms two terms that are not synonyms. The two terms are extreme and outlier. But I will stop here. We will talk about that again in a couple of weeks. In the meantime, I recommend an interesting book, The Case Against Reality by Donald Hoffman. It is a book that, starting from the cognitive sciences, seems to excellently support the idea of subjectivity as defined by Bruno De Finetti. We will discuss it further. Alright, goodbye then. Ciao ciao.
Ryan Seacrest here. When you have a busy schedule, it's important to maximize your downtime. One of the best ways to do that is by going to ChumbaCasino.com. Chumba Casino has all your favorite social casino games like spin slots, bingo, and solitaire that you can play for free for a chance to redeem some serious prizes. So hop on to ChumbaCasino.com now and live the Chumba life. Sponsored by Chumba Casino.